Okay, do this, please. Solve that differential equation. Second order differential equation. Why is this a second order differential equation? Because it's a second derivative.
Oh, this is the one that I asked you guys.
Yeah.
You didn't put anything around the zero. Or
You're right. Equals, let's see, what's that equal? That one equals 0.
So it's pretty much.
Well, we got to know what it is. Okay, so what do we do with this? If I want to solve a second order differential equation, our goal, remember, is to undo the differentiation part. We want to find f of x, the function that's going to give us this result with these conditions when we differentiate twice and get a second derivative, right? Okay, so what do we do? What's the first step here? Okay, first step. Okay, we have anti-differentiate, right? So we have to do it one piece at a time, though. The second derivative is just the derivative of the first derivative, right? So yeah, I could find the first derivative by doing this, right? By anti-differentiating the second derivative.
Yeah.
Okay, and if we do that, well, we have a function for that. Okay, what is that antiderivative? It's just power rule, right? You fill in the blanks. What goes where?
It's a C.
Okay. There's contribution. You're off the clock now. Somebody else, though, what's the harder part? What's the power going to be? Negative 1/2. Good, because we're going to have to, because remember, our power for integration or anti-differentiation, we're adding 1 to the exponent instead of subtracting 1, right? So I get x to the minus 1/2 over negative 1/2, right? But we really don't want to divide by a fraction, do we? Instead, what would we do?
Over n plus 1.
Right? Instead of dividing by negative 1/2, which is n plus 1, negative 3/2 plus 1, I'm going to multiply by the reciprocal, so by negative 2, right? Okay, now that's pretty good, but we want to know what that constant is. How do we find the value of the constant? Ah, okay. Guy right there, right? That particular condition is telling us the value of f prime when x is 4, right? So I can plug 4 in there, and it tells me that this whole thing then is equal to 2.
You mean 4?
Whoops, 4, you're right. Which is a lot more convenient, isn't it? Okay, so what is 4 to the negative 1/2? What's the 1/2? What's 4 to the 1/2? 2. What's the negative part do?
1 over 2.
Puts it on the bottom. Yeah. Negative exponent on top is positive on the bottom. So I end up with 2 equals negative 2 over 2, right? And that's just this part right here becomes that. Plus C1. So negative 2 over 2 is, okay. So then, what's C1 equal to? 3.
Oh.
Because I'm going to add 1 to both sides. This whole thing just becomes a 1, doesn't it?
Negative 1.
Negative 1, but then I'm going to add, I have to add 1 to both sides. Okay, so I get C sub 1 equals 3, Okay, and that's good. Now I know what f prime of x is. We got to keep going. So if f prime of x equals negative 2x to the minus 1/2 plus 3, how do I solve for f of x? Well, but I have, right now, I've got an f prime of x. How do I? Good. Okay, so I'm gonna take an integral here, and I get f of x equals, I'll leave the negative 2 out front, might as well. Leave the constant out front. Okay, now that 3, that plus 3, actually, hang on a second here. I can't really do it that way, can I? I have to be a little bit careful with this. I just did something kind of careless there. Well, because that seemed to imply that that 2 was being multiplied by the whole thing. And it's not, is it? Right. So,
Either way, it goes 1.
so it's, yeah. But I probably don't want to pull that negative 2 out front then, unless I'm really going to split this into 2 separate integrals. Either or. Yeah. So I'm going to undo that. Not be so tricky. Just do that. Right? Does that make sense? Okay, so now we'll just integrate term by term. What about the first one? So the antiderivative of negative 2 x to the minus 1/2 is negative 2 times what? What's the antiderivative of x to the minus half? X to the 1/2 divided by 1/2, right? Which would be the same thing as times 2. Okay, and then I've got the plus, antiderivative of 3 is 3x plus, call it C2. Okay, now we have the other condition here that f of 0 equals 0, right? So if I plug 0 in for x, that should equal 0. Okay, because let me draw a circle for you. Because this stuff, the antiderivative of that is going to give me back that, right, by the power rule. The antiderivative of x to the minus 1/2 is x to the negative 1/2 plus 1. So n plus 1, x to the 1/2 divided by 1/2. But dividing by 1/2 means multiplying by 2.
Oh.
Right?
Does
Does that make sense?
Yes.
Okay, so then if I, now 0 to the 1/2 is just 0, so that term goes away. 3 times 0 is 0, so I get C sub 2 equals 0, right? So the second constant is 0 valued, and so then our answer is just this, right? Okay. So negative 4 times x to the 1/2, or square root of x, plus 3x. Right?
Yep.
Okay, good. Okay. Okay, so I think we're good with that stuff. I want to introduce one new thing here. We've gone almost all the way through 4.4. Remember, in 4.4 was a really important section. 4.4 is where the most important thing we did in 4.4 was the first fundamental theorem of calculus. That's the one, definite intervals, the trick, right? So real quick, just to make sure we're all on the same page with that, we could find the area under the curve x squared from 1 to 7 by just anti-differentiating, right, and evaluating the antiderivative from 1 to 7. So that's going to equal x cubed over 3 from 1 to 7, which is just 7 cubed over 3 minus 1 cubed over 3, and that's our answer, right? That's the area under the curve. Okay, so that's the big ticket item for 4.4. That's the most important thing That's huge. We also talked about the mean value theorem, right? And all we said with that, with the mean value theorem, for integrals at least, is the area, if I, tells us this, it tells us that the average value of a function, we called it f of c, remember this stuff? Just equals the area under the curve over its interval. If we say, let's say we're going to define the interval as going from a to b. Those are the x values that define the interval. So the area under the curve divided by the width of the area gives us the average height, right? So that was our mean value theorem. Okay. And last part, last step of this then. Here you go. Are you everybody done with that? Gotcha. Okay. So last part is what we call the second fundamental theorem. Now, I'm going to give you, this is a pretty good deal you're getting here. I'm giving you something. The second fundamental theorem is not really described this way, but this is a great way to do it. Second fundamental theorem, and if you look in the book, here's all it says. Okay, now let's take a second and think about what this means. Okay, now let's focus on this part right here for a second. Okay, what does that mean? That means that we're adding up the area under some curve f. This describes the function, right? So if I were to graph this thing, this is kind of a weird concept. I'm going to graph on the t-axis, right? I've got the t-axis, and then I'm graphing the function f of t. So there's f, right? F of t. And we're adding up the area from some fixed left boundary, so that's going to be a, up to x. But x is a variable, right? And so if this end is x, then you can see that I'm sweeping out area, but as x changes, the area is changing, right? Isn't that weird? Okay. That's a really pretty interesting and important thing to be able to do in calculus, though. We can take what's called a dummy variable, t, which we're going to use to define the shape of the curve, and the variable x we're going to use to describe the area, because it's, or to regulate the area, because it's controlling where we stop adding up area. Okay? Now, you can see then that this area under the curve, this truly is a function of x, isn't it? Because as x increases, this area function up here is changing also, right? And what I really probably should say is call this capital F of x, not small f of x. So if we differentiate this then, if we find the rate of change of this area as a function of x, that's going to depend on the shape of the curve, right? Because if I'm sweeping area out over here where the function is not very tall, as x moves along, let's say at a constant rate, the area is not growing as fast here, is it? As it would over here where the function is much taller, right? As I move along, I'm shading bigger portions under the curve because they're so much taller, right? For every centimeter that I move, I'm just getting a tiny little piece here, but a pretty tall piece here, right? Make sense? Okay, so then doesn't the rate of change, and that's all the derivative is, right? When we say what this really is here, if we want to say this in a good calculus way, we're saying the rate of change of this integral with respect to x. So how fast is this area we're defining changing with respect to x? Shouldn't that then depend on the shape of the curve? Yeah. It should. It should depend on the shape of the curve, and it should depend on the value of x, because if x is out here, we're going to get a bigger answer than we would back here, right? So is it surprising then that this is our answer? No. It's not at all, is it? I mean, that makes sense, right? Where f is bigger, right? Does that make sense? Where the function is taller, at those x values, the rate of change is going to be bigger, right? Okay, so then these questions are really easy to do if they're set up to match this perfectly. For example, and this is the way they do it in the book. What if we had, if I want to know what's the rate of change of the integral of x squared, well, actually I want to do t squared, hang on. From negative 13 to x. Okay, what's that equal to? Does it matter where I start this thing, by the way? If I'm finding the rate at which the area is changing as I move x along, does it make any difference where I started adding up the area? Shouldn't, right? It doesn't matter if I start here or here. As I move along, I'm still sweeping out the same pieces of area, right? It's irrelevant how much I've added up over here. All we care about is how much green area am I adding for a little shift in x, right? So the first, it doesn't matter where I put a. If it's constant, then the rate of change of area only depends on x, right? Okay. So for a problem like this, I don't care what that is. It's constant, right? So this matches the second fundamental theorem. If I differentiate the rate of change, right, I'm taking the rate of change of this function of t, right, this integral, definite integral of f of t dt from some constant up to x, well, the answer is just f of x. So what's this one going to be? All it depends on is the height of the curve at x, right? So what's the answer? Okay, but what's f of t in this case? T squared. So the answer is just x squared. Right?
Wasn't it?
Well, f of x is x squared.
Oh,
You see what I'm saying? F of t is t squared, so f of x is x squared. The only thing that the rate of change of area depends on is the height of the curve at x, because that's where we're taking the snapshot. As this thing is moving along, we're taking a picture right there when the right edge of the area happens to be at x. And so that's how high the function is there, right?
So no matter what like the function is, besides like t squared, it could be like some other thing. Just replace t with x.
Yeah, let's try another one.
You're using x's.
Whoops. Thank you.
Anytime.
Okay, what's the answer to that?
X.
Yeah.
I
didn't get that. I wonder what it was.
Don't you just replace t with
Yep.
x? So everything in there is like x.
That's it.
I will get this example.
Okay, now don't even look at that yet.
Okay.
Don't look at that yet. Okay, so now what happens if we go back here to our picture and we say, okay, now this time we're gonna look at the rate of change under the curve, but not from a to x, but we're gonna look at the rate of change from a to say x squared. Okay, now that's going to change things a bunch, isn't it? Whoops, we've got snags. Someone's setting up a snare for me up there. Okay. Now that's going to change things, isn't it? Because now would you agree this is going to make things much more complicated? Because now we want to know what's the height of the curve going to be, out here at some value of x squared, right? And as x changes, then not only is the height of the curve changing, but where we're stopping the interval is also changing. It's not just x; it's at x squared, right? So if I were moving along at a rate of, let's say, 1 centimeter per second, and I want to know what's the rate of change of this function from a to x squared, well, now all of a sudden the rate, if this is where x is increasing exponentially. X squared is, right? If we start at 0, when we're out here at 1, when x is 1, well, x squared is also 1. But when x is 2, x squared is all of a sudden out here at 4, right? Right? You see what I'm saying? So it's changing in a very complicated way. Okay? It's changing in a way that now it seems like this would be really difficult, but it's not.
But don't you just replace the t's with x squared?
No, what you have to do then is we have to use the chain rule. We have to use the chain rule because we're going to go from, if we're going to go from a to x squared, then we have to know what the height of this thing is going to be at x squared, but we also have to take into account the rate of change of the x squared itself. So we have to differentiate the x squared, right? Because we have to know not only how is the curve changing out here at x squared, we've got to know how fast is the right edge of that area moving along the x-axis or the t-axis.
Isn't it just
Right.
moving along x squared?
And, well, so what it amounts to is simply doing the chain rule. So here's the ultra generalized. Or actually, we'll start with the generalized. How about? If we start with the generalized second fundamental theorem, which, as far as I know, I've never seen this in a book, but this works. This is a good thing. I mean, I treasure this dearly because I don't know where, I've never seen it anyplace else, but it definitely works. I'm 100% certain it works. It just makes life a lot easier. Otherwise, you have to reinvent this process for every individual problem that you do. This is a very general thing, though. It always works. All it is just simply, it's like fusing the chain rule with the second fundamental theorem. And the meaning of the chain rule exactly fits with what we're doing here. Now I'm going to shut up about that and just show you an example. So here it is. Here's the generalized second fundamental theorem. The derivative with respect to x of the integral of f of t dt from a to, call it g of x. Could be any function we want. Could be x squared, could be a sine function, could be anything.
It's h of x.
You're looking at the bottom one.
Yeah.
Okay, equals from just like before, right? Now watch this part. Just like before, it's going to equal the value of f of t evaluated at the right-hand limit. So it's f of g of x. But instead of being times, just times 1, it's going to be, we have to take into account the fact that this thing is moving along at a rate that changes. And so the rate of change of this upper limit itself has to be accounted for. So we just multiply by the derivative with respect to x of the upper limit. That's telling us, all that's saying, I know this is getting to be a lot, but just hold this thought for a second. The derivative of g of x, or g prime of x, all that is the rate of change of g of x with respect to x. You see what I'm saying? Okay. So times g prime of x. So as we're sweeping out the area now, there's f, right? Here's our fixed, call that a. And then out here is going to be x, right? And let's call this x. Okay, so then let's call this g of x, right? So we're actually adding up that area, right? That's the area under the curve. So the height of the function, we need to know the height of the function here, but we also have to know how fast is that edge moving. That fast. Okay.
How fast is that moving back?
How fast is the right edge of the interval migrating along the t-axis tells us that contributes to how fast we're adding area, right? And so that's how fast that point is moving. Okay, so that's it. Now let's try one of these. You'll see that these are really simple problems to do. Okay, so then let's take an example. What if let's do this. How about oops. How do you do that? Okay, so there's my area function, right? We're adding up the area under the sine curve from -1 to x squared. So what if we want to take the derivative of that? We want to find f prime of x, right? Take the rate of change of that area. Same thing as saying the derivative with respect to x of this whole thing, right? Okay. Well, that should just be equal to then the sine function evaluated at x squared, right? Times, times 2x, the derivative of the sine of x squared. That's it. That's the whole answer. We would, if we want to write that a little more cleanly, we'd write it as 2x sine squared, sine of x squared. We put the 2 out in front and then the x and the trig function last, but that's just a matter of housekeeping. Didn't change anything.
Oh, that's pretty easy.
Yeah, it's not hard, is it? Okay, now what's the last part of this? And this is so above, I mean, it's way beyond what the book does, but I think it's really, you'll be glad you saw this. What if we go back to our original picture? Now, we stated that A was going to be fixed, but it doesn't have to be. We could be sweeping out area from the left side also, right? Does that make sense?
Yeah.
I mean, we could be changing both of these boundaries simultaneously, in which case the area would be changing at an even more complicated rate, right? But all we've got to do is this. Okay, let's start with an easy one. Let's say we've got start easy here. So we're going to take. Here's our area function. Okay. So we're gonna change both of these. Right, we're going to be going back in the opposite direction. When x is 10, the lower limit would be -10. The upper limit would be 10. When x is 1 billion, the lower limit, left limit would be -1 billion, upper limit would be +1 billion. So now we're adding up area in both directions, right? Make sense? Now, I happen to have picked a symmetrical curve, but what if I didn't? The contributions from either end could still be different, right? Make sense? In this case, they're the same because it's symmetrical with respect to the y-axis, but the odds of that weren't good. Now look what we can do with this. This is pretty cool. We can break this up by our properties of definite integrals. We could split this up into 2 integrals. We're just going to pick some value a, could be anywhere. Just to make things nice and neat, let's say it's somewhere between -x and x. I mean, we might pick 0, but it doesn't matter what we pick. It just has to be constant. Isn't this true? Can I say that say that?
You can.
Right? I'm adding up the area from -x up to a, and then the area from a to +x, and the sum of those two areas would be my original area. Just breaking it into two pieces is all, right? Okay, I can also say this, can't I? Can't I also say here that this one, if I flip the limits of integration and I go from a to negative x, all I'm doing is put a negative sign out front, right?
Yeah.
Okay?
Yes.
Whoops. Okay, I think this is going to do what I want it to do. That's nice. Okay, so then, what's the answer to this? What's the answer to this part? That one's easy. This stuff all becomes what? If we differentiate this, sorry, we're going to take the derivative of this whole thing now. So this is f of x. Let's find, I'm going to add a little bit up here. Find capital F prime of x, right? So we're differentiating this whole thing. Okay, so what about this? The derivative of the second term? That's just that formula we got, right? Second fundamental theorem. The derivative with respect to x of f of t dt from a constant to x is what? Say it again? But not t, x squared, right? Yeah. So this part becomes x squared, right? What's this part going to become over here? This part is going to become, the quantity negative x squared, right? But I've also got this minus sign out front, right?
Yes.
So I could turn that around maybe more conveniently and say that's really just x squared minus, and that minus has to be there because we flipped the limits of integration, right? Minus negative x squared, right? Okay, so then really all we did is we just took the answer to this integral, the rate of change of this integral, minus the answer to this one with the limits flipped, right? We could do that every time. In fact, if we want to turn this generalized one into an ultra-generalized one, we can just say this. The derivative with respect to x of f of t dt from, call it, what did I say, h on the bottom, I can't remember what I said. H of x.
Yeah, then G of x.
Is just going to equal the top one, right? So that's going to be f of g of x times g prime
Minus f of h.
minus, same thing I would get if I flipped the limits around, if I cut this interval at a constant and flipped it around. So I'm just going to have minus f of h of x times h prime of x, right? Okay, where's that minus sign coming from?
When you flip it.
Yeah, when I do the switcheroo, right there, exactly. Okay, but you don't have to know any of that. All you have to know is that's the formula you use, and it works. And you can do the most complicated conceivable. I tell you what, this is probably. I'm not kidding. This is, if you were to take a big time math test, like say you're going to take the SAT calculus specialty test, this, if they have one.
They do have one.
I think they do. This is the problem right here that only 2% of the students would get right. But if you know this formula, you can do it so quickly. That's the easiest shortcut I could possibly give you for any calculus problem. It's that one.
Not easy math.
No, it is. I mean,
Any
the
math problem
alternative.
ever.
What's that?
Any math problem ever.
I have yet to see something that you can
How do
simplify
you
that.
find 1 plus 2?
Well, 1 plus 2 is pretty easy to begin with.
Well,
Yeah, but you said
You don't know.